My name is Nick Ishmael Perkins, and I'm the editor-in-chief at C&EN, and I'd like to welcome you to our inaugural Future of Chemistry panel. We at C&EN have decided that we'd like to do a series which focuses really on bringing together some of what we see as the key thought leaders in the global chemistry enterprise to reflect on the past, to provide some insight and also some foresight about what we see as key issues that will be affecting the practice and policy around chemistry. And I am really excited about what we have planned for you this afternoon. And if you wait until the end of the panel, you will also hear a little bit about some of the other events that we're planning around this idea of hindsight, insight, and foresight. But for the next hour and 15 minutes, I'm very pleased about the conversation that we're going to have around something which the NSF has identified as having the potential to be revolutionary for the practice of chemistry. And this is the future of chemistry with quantum computing. And I am particularly pleased with the panel that we have put together for today's event. And we have Professor Todd Kraus from the University of Rochester, who leads his own research group on nanometer materials. And what is particularly exciting, I think, about having Todd here today is that his group works with highly interdisciplinary teams working across chemistry, physics, applied physics. And I think this bodes well, not only for the way that we think about our audience at C&EN, because these days chemistry news is not just for chemists, but also in terms of the breadth and the depth of conversation that we're going to have this afternoon. And with that, I'd like to invite Todd to lead the proceedings.
All right, well, thanks, Nick, and thanks to you all for joining us this afternoon for this discussion, exciting discussion of quantum computing and how it intersects chemistry. We're going to hear from our panel in a second. The way this will play out over the next hour and 15 minutes or so is we'll have some kind of prepared questions. We've prepped the panel here a little bit on just what is quantum computing, catching everyone up on that, how that intersects chemistry, maybe where it may be going in the future. If you have questions, park those questions for a little bit. We definitely will have some time for audience participation and questions where you can pepper the panel with your own ideas and thoughts. Okay, so without further ado, I'll let the panelists tell you a little bit about themselves, where they're from, and how they intersect quantum computing, starting with Jeannie over here.
All right, thank you. So it's on, yeah? You guys can hear? Okay. I'm Jeanette Garcia. I go by Jamie, though. I was actually just answering the question, how long have you been coming to ACS, and realized it's been since 2002, so 23 years? That's crazy. Anyway, so my background's in chemistry. I have a PhD in wet chemistry, actually doing organic chemistry, and then I moved to IBM to start looking at materials and polymer chemistry about 13 years ago. And then about 10 years ago, I got very interested in quantum computing and what it might actually be able to do for chemistry in particular, and was inspired by some results that I saw in the hallway in Yorktown Heights, which is our sort of crown jewel, if you will, of locations for quantum research. So that's how I got interested in quantum. That's why I'm here and excited to talk about chemistry today.
Great.
So my name's Nathan Baker. I guess we should all start with how long we've been going to ACS meetings now, huh? So I've been, I think my first ACS meeting was 1997, and I've tried to attend as much as possible since then. I love the American Chemical Society. So my background's chemistry. I did my PhD here at UC San Diego, so it's great to be back in San Diego. And from there, I was in academia for a while at Washington University in St. Louis, and then moved on to Pacific Northwest National Lab. I was there for 12 years. And that's where I got interested in quantum computing. We started a collaboration with Microsoft, University of Washington, and really started to see the potential of this technology. And like Jamie, the first impact it's going to have will be chemistry, right? So it was just perfect for a chemist who's a computing geek to, see what's coming. I moved to Microsoft about 2.5 years ago. I'm a partner in Microsoft Quantum, and I lead the engineering team focused on quantum applications.
Good afternoon, everybody. I'm Laura Gagliardi, And as you can hear from my accent, I'm not from the US originally, I'm from Italy. And for this reason, I have started attending ACS conferences later than these people. It doesn't mean that I'm younger, but I just moved to this country only in 2009. So since 2009, I've been very faithful to these meetings. So I am a theoretical chemist. I had my education in Italy. I started my career in Europe in various places, and I moved to the US in 2009. I was at the University of Minnesota first, and since 2020 at the University of Chicago, where I am professor of chemistry and molecular engineering. I am a quantum chemist. I originally, of course, we are interested not just in molecular systems, but also extended materials, also because I think there is no bridge between molecules and materials. I look at everything with the eye of the molecule, with the eye of the orbitals. And of course, over my career, we have worked with classical computers to develop strongly correlated methods and apply them to chemically relevant systems. And nowadays, of course, we are looking with interest to quantum computers. I think that what has been very important for my career and is always talk to experimentalists, so not just work as theorists in our bubble, but be challenged by real chemistry and material science problems so that we can bring our methods to the next level. I want to finish by saying that I'm also very connected with the American Chemical Society because I'm the editor-in-chief of a Journal of Chemical Theory and Computation and together with Kenny Mertz, who is the editor-in-chief of Journal of JCIM. I think these are the best theory journals, modeling journals in the world, and so I encourage you always to submit your excellent paper to our journals.
All right, thanks very much, panelists. Now that you know them a little bit, it's time to get to some questions. So I think I know what a classical computer is, right? It's based on a CPU, fundamentally derived from bits of silicon that are, doped negative or positive that become transistors. Those transistors go to logic, and on, right? What is a quantum computer? How does it work? Someone want to take that?
Well, a quantum computer. Okay, so it is different from a classical computer, first and foremost. I teach my 3.5-year-old daughter that the opposite of classical is quantum and vice versa. So she already knows those. But yeah, so basically quantum computers operate under the principles of quantum mechanics. So it's a fundamentally different way of operating. As a chemist, you can make the leap and say, okay, and this is sort of the first vision of how you might use a quantum computer is that in the simulation of nature space, it operates under the same principles, so therefore you should be able to use these qubits to be able to perform operations and calculations to simulate nature. Qubits are fundamentally different than classical bits. Classical bits you typically think of as being in a 0 or a 1 state. It's an off or an on kind of mechanism. Qubits, however, can exist in a linear combination of different states, which means then it kind of scales with a 2 to the n kind of exponent for the amount of states that you can access in principle for any series of calculations. The way that you operate these is by basically influencing them. So we actually at IBM work on superconducting qubits. So these are made with superconducting as opposed to semiconducting materials, which allows us to access these properties. They're cooled to around 15 millikelvin at their coldest state. They are very sensitive. When you put the qubits in the state, they're sensitive and they can kind of fall out of the state, if you will, if it's exposed to anything like heat or any sort of outside influence, right? So they're contained in refrigerators at around 15 millikelvin. And then you can perform operations on them by putting in different microwave pulses to basically influence the qubit and move it into and manipulate it into different states that you want it in. And when you kind of combine these all together with a series of qubits, you can conduct something called a quantum circuit, which then allows you to carry out algorithms and operations of interest. So that's, in a nutshell, what a quantum computer is.
Anything to add?
Maybe you want to add. No, I'm more on the chemistry side. You are the expert.
That was pretty thorough. But maybe I'll just add some random things. So the first is that one of the reasons I think there's so much excitement about quantum computing is that computing hasn't changed fundamentally since the abacus, which I think is like 2500 BC, right? So 4,500 years of computing the same way. And it just opens the imagination to think about, how do you harness the power of this new way of computing? How do you harness what a quantum mechanical representation of information can give you, especially in exploring really large search spaces, most of which appear in chemistry, material science, and of course other applications. So it's exciting. Since you mentioned the superconducting qubit, I'll also talk about, there's a whole family of qubit types out there, a whole family of technologies, and I think it's equally exciting to see that we're at kind of where classical computing was in the early days, where there were vacuum tubes and the transistor was starting to show up. There's superconducting qubits, there's neutral atom qubits, there's trapped ion qubits, there's topological qubits, there's photonic. There's so many out there. It's fun from a technology excitement perspective as well, not just to see what quantum computing can do, but to see all of this technology mature in parallel.
On qubits and computation, again, so when I was a student a couple of years ago, okay, more than a couple of years ago, but I actually built a little computer, right? I had transistors and I put them and I made logic operations and I sent some code, probably an assembly, to those logic, circuits, and did computations. How does one compute? What is being sent to the qubits and what is being extracted from the qubits to perform a calculation?
Well, I think you started to touch on it, right? I mean, the first step is to load information into the quantum computer, prepare a state, right? Yeah. There's many ways to do that. Some of the technologies use analog signals. We're excited about the topological approach because it uses digital signals. But either way, you're loading information into the quantum computer, which is not cheap. It's actually hard to turn classical information into coherent state on the quantum computer. And then depending on your approach, you either take a gate-based approach, which is typically what we focus on. So you apply logical gates to 1 qubit, 2 qubits, sometimes 3, and move the system forward by an evolution of these logical gates, manipulating the qubits. But there's also analog approaches too, where instead you think of the system as some big complicated Hamiltonian that evolves in time. Either way, some calculation progresses, and then you read out the information at the end, all the while trying to figure out how to deal with the noise that Jamie mentioned in the system that can confound some of the calculations, and you need to be thinking about error correction, which I'm sure we'll talk about in a bit as well.
Yeah, and I was just thinking about what I wanted to add to that too. So there are gates that are analogous to sort of like a classical way of thinking about it. And then there's certain things that with a quantum computer that you just don't have any classical analogy for. So entanglement is the main thing. So we have something called a C-knot, where we basically are able to entangle 2 qubits together. And what this, I don't know if you guys know what entanglement is. It might be useful to describe that very briefly. But basically, it's the premise based on, again, quantum mechanics, that if you have a qubit in a state, the second qubit, once it's entangled, no matter how far the distance, right, it can be galaxies away, will have the exact same state. So you by default know the state of qubit 1 if you know the state of qubit 2. Right, so it's superposition, which is a unique kind of feature. So this ability to be like in a 0 or 1 state or a linear combination of states, right? It's entanglement, and then you also have interference too as a possibility, as a sort of a knob you can turn when you're thinking about how to algorithms and how to set up your problem on a quantum computer and the circuit that you want to run. The interesting thing about quantum is you can have negative interference as well. So it's not just positive interference. You can think about it like waves crashing together, and then there's also sort of a negative version of that as well. So that is fundamentally how you program a quantum computer. You need to design the circuit, the degree of the circuit that you can run. And oftentimes we call it, like, you think about width, so number of qubits that you need, and then depth, how many times you have to run things over again to get the answer that you want. That complexity is, and the degree of complexity that you can run is highly based on the quality of the qubits. So it goes back to this idea of noise. How long can you keep something in that very fragile state that you want to put it in so that you can run your operation in your circuit that you're interested in? And this is very relevant for chemistry because a lot of the circuits that we're interested in running for chemistry have very large depths. And so in other words, the better the coherence, the longer that you have the options to run these, the better your answer is, and the bigger circuits, the bigger molecules are that you could possibly run. So that's just another thing to note, is that as the technology continues to improve, as the hardware begins to be able to improve past a certain point, you're going to be able to run larger and larger circuits of interest. And I think we can probably talk a little bit more about that later.
No, I mean, I don't want to enter into. I think what you said is perfect. My question was perhaps also, so the audience can also resonate in those terms. When you say when we want to do chemistry on these quantum computers, what do you exactly want to do? And I may have some examples, but maybe you also had something in mind specifically. What kind of chemistry?
So, yeah, my dream, right, so I came from sort of the background of working in the lab and running experiments, and I worked very closely with some of my really wonderful computational chemists that we had at Almaden in San Jose, some of whom are in the audience today. And I think that, you know, sort of the best work that we had ever done was an iterative approach, right? Where basically you started with an experiment in the lab, you had some observation. Sometimes it was a weird observation, like it was something that didn't really make sense or that we weren't predicting or we weren't trying to do. And so we would go and talk to our computational chemists like to bring in the theory and really define like what the mechanism is and try to narrow it down. And then you go back and forth and you try different experiments to confirm that that is the mechanism in fact. And then once you have that together, then you can publish it, right? As like at least an idea, but there's nothing guaranteed about that. It's still a best guess in many ways, right? So I think that for me, like my personal dream would be to see something, and it's a holy grail kind of situation, where you can go to, you know, your computer, and maybe you don't even know what's happening behind it, but there's quantum involved in the workflow somewhere. It's probably HPC plus quantum. Maybe you have some AI elements, whatever it is, but you have your interface. You go, you plug something in before you go into the lab. It gives you an answer, and you have enough confidence in that answer that you can either go back to the lab and try it and think you're maybe only going to run an experiment once or twice, or, you know, or maybe you just take that as the answer, you know, in an ideal world. So that's sort of the dream and the vision of what I think, you know, quantum could potentially bring to computation and to chemistry as a whole and as a science.
So you are thinking about using a quantum computer for a quantum simulation, and because, for example, I mean, there is also this interest in quantum sensing. And in principle, one could generate a qubit that makes these super sensitive measurements. And so that is not like a simulation; it's more like an experiment. So, for example, I have a collaboration with a colleague of mine at UChicago, Peter Maurer. He wants to make these molecular spin qubits in a protein. So use the protein as an environment to create these two-state systems that, I mean, can be used for very sophisticated measurements. Yeah, that was another type of possible utilization. Mm-hmm.
Yeah, it reminds me of the joke that there's no such thing as a bad qubit, it's just a good sensor, right? So I think, yeah. We're very focused on quantum computing, and I think Jamie really hit the three pillars that are going to impact chemistry the most. Quantum computing will be an accelerator, and it'll live alongside high-performance computing for physics-based calculations, and AI that accelerate those physics-based calculations and get better from the data produced by a quantum computer. And then the opportunities in chemistry are almost endless.
So this gets into another one of my questions. I'm going to poke you a little bit. I have a classical computer. My kids have a computer. You know, they play FIFA 25 on it. You know, they're very happy. What makes a quantum computer better? than a classical computer? You know, is it going to be better for everything, or only for a small subset of things that maybe in this room we care about, but the world won't care about? Or, you know, overall, how do you see computing getting better with a quantum computer?
Yeah, so I think there's I think of it as like three big buckets, right? So quantum computers are not going to be better at all tasks, right? Versus classical. So if you want to do like simple addition, you probably don't need to use a quantum computer for that. But if you want to do factoring, you probably want to use a quantum computer for that eventually. So the three big buckets that I think of are simulation of nature, and then mathematics and processing data with structure is another one. So this is like Shor's algorithm. You guys have probably heard of cryptography and like breaking RSA, that kind of thing. Falls into that category. Also quantum machine learning falls into that category as well. And then the third bucket is search and optimization. And so search and optimization, I think of the three, like all of these have someone with intuition has sat down and looked at it and said, like, I think quantum computer could probably play a role here and could probably, reduce maybe the computational resources required to run solutions to my problems, right? In the first two buckets, there's actually evidence that we have something called super polynomial speed up available. So it's really, really, really big, basically, is what that's meant to say. And then in the last category, there's a quadratic speedup on paper that we think we can achieve with the search and optimization type of approaches. So you can imagine all three of those buckets. They actually impact a lot of different industries across the board. Everything from finance to pharma to healthcare, life sciences to you name it, basically logistics problems. So I think that has a very wide range of different impact as a potential, and that is where we think the promise of quantum really comes. And the secret is always in how you design the algorithm and how you design the circuit and how you map it onto the quantum computer. And so that really, you have this theoretical guidelight saying, like, we expect some sort of speed up possible using quantum algorithms, using and leveraging the three things that I mentioned earlier to be able to run a calculation. And then you kind of couple that with what is happening and like today, error mitigation techniques, the potential for error correction in the future, the way the qubits are designed and everything else. And those things coming together is where we think the highest impact will be.
I think you summarized it very well. I will say we have a slightly different perspective on those three buckets. So we've been interested in a practical quantum advantage. And if you think about a quantum computer, it's going to be slow. It's going to run about 10 to the third logical operations per second. You compare that to a GPU, it runs on the order of 10 to the 15th logical operations per second. So when you look at scaling, of the different algorithms and the speed up they provide, we're really focused on those super polynomial scaling type of speed up problems. You can think of them as exponential, where we know the classical problem is going to scale exponentially in problem size, and there's hopefully some polynomial algorithm that will scale that way on a quantum computer. That's important because if you start to analyze the crossover points between a quantum computer time to solution and a classical computer time to solution, you look at where they cross over. With that amount of difference in clock cycle, for the quadratic speedup, they may not cross over for a year or a century or a millennia. And so for us, my patience isn't that long. It makes me think of the Douglas Adams novel where they ran the computer for a long time, got 42, forgot what the question was, right? So we're really interested in those super polynomial speed up ones, and also equipped with small data size. Loading data into a quantum computer is hard. The clock speed hurts you there as well. And when you apply those filters, guess what? You end up with chemistry. You also end up with factoring. But this is one of the reasons we're so excited about chemistry in this space.
Now maybe we can talk about some chemistry examples.
Yeah, I was going to toss one over to you, Laura. So, like, if I'm a new student, graduate student, and I see theory is probably where you're going to intersect quantum computing first, what areas of chemistry should I be thinking about if I want to work with quantum computing?
So, first of all, let's talk about modeling and computational chemistry with classical computers. And I think that we all know that this is really a fundamental part of chemistry. And nowadays, most papers that come in ACS journals and in all journals, chemistry journals, they really have strong chemistry components. And so, for example, if we think about quantum chemistry, because we are breaking bonds, forming electrons, and this is probably what is most interesting for this technology. The workhorse of computation nowadays is density functional theory, which is great. I mean, it's used in drug discovery, catalyst discovery, materials discovery, especially in combination with AI.
Nobel Prize as well, right?
Nobel Prizes, yeah. And yes. And so the question is that there are some chemistry problems where sometimes DFT doesn't give the right answer, or if it does, it's fortuitous. I mean, you can always find a DFT functional that eventually will give you the right answer, but there is not a systematic way to improve it. If you want to, and these are systems where we talk about strong electron correlation, which for physicists and quantum chemists means different things. But let's say that you want to study a catalytic mechanism where you have a transition metal catalyst, and along the reaction, the electronic configuration of your system with a d or some d electrons change, and or you have an organic chemical reaction and you have radical species along the way. I mean, these are situations which we call them strongly correlated, in the sense that there are many electronic configurations that are all equally important and they should be included in the description. And DFT chooses one of them. It chooses it very smartly, but it chooses one. So it's a static picture. So these methods that are more wave function based methods, they are very important to describe this challenging chemistry situation. And this method scales exponentially, and so on classical computers, I mean, you can study small systems and middle-sized molecules, but let's say that you want to study more extended, a chain of molecular qubits with many transition metals. You want to study a material, or you want to study a chemical reaction, and so these calculations are not very efficient on a classical computer, and perhaps they will be one day on a quantum computer. I think that exascale computing is really very powerful nowadays, and we can run some of these calculations with the software that has been optimized for GPUs effectively. But I think combining exascale computing with quantum computing, at least for a portion of this hard task, is the way to go in the future. I have to say that I want to be very honest with you. So, sorry, maybe it's not. I'm just saying that it's not solved, the problem, okay? And as a quantum chemist, a computational chemist, we always look at the real world. And at the end of the day, when we try to develop an algorithm for the quantum hardware, or the quantum simulator, we look at toy systems that are an embarrassment almost. But at the same time, you know, it's like going back to the 60s, when quantum chemistry started on the computers. They were looking at the hydrogen molecule with a minimal basis set. And that's what people do nowadays on a quantum computer. And so I'm just saying that it's the right way to do, because you have to start small. But saying that nowadays we can solve catalysis problems, climate change problems, drug discovery problems on the quantum computer is an illusion. It's a promise. It's not happening right now. I hope the other panelists agree with me, and I don't destroy their business, but I think we have to be honest.
I don't think it destroys our business.
Okay, good.
I think the exploration is the interesting part here, you know, because we're starting at a point that you can imagine was, like you said, in the 60s or something like that. You have access to a tool for the very first time. You know, students have access to a quantum computer on campus at RPI, for example. They're starting to do things and tinker with things, and we're talking about, like, we were talking about the applications, things that we think will happen. I actually am going to be very interested to see what comes out of this generation, because I didn't have a quantum computer growing up, and it'll be really interesting to see what they end up doing. And who knows, the use case might be something totally different than
we don't even know what the killer application will be.
Right, right. The other thing I do want to kind of say is that I think that even so, the rate at which things are moving is just astronomical. It is mind-blowing to me. Watching the hardware evolve to the place that it has evolved to now, what we're talking about, I mean, at IBM, we're saying we're going to have 200 logical qubits available in 2029. That's a huge deal. You can actually start running error correction on these systems, right? That's a huge stepping stone. The other thing that we're seeing at just an absolute massive pace is the rate of the algorithm development and the creativity that comes with the algorithm development. So Shor's factoring algorithm, which is one of these that have the exponential proof speed up with it, just recently, there was a new variant that came out of it, a couple of different papers that came together that basically reduced the circuit size by orders of magnitude. And it was sort of a parallelization technique and included classical post-processing that was really important. Again, HPC plus quantum really need to work together. And those kind of things, like, we don't even know what's going to come. So these things that we think have huge circuit sizes, the algorithms, it might actually require smaller circuit sizes. So that's important to remember. The other thing is, too, I mean, even just this year, you know, talking about like transition metal chemistries, I mean, our team published on iron sulfide calculations. And I wouldn't have, thought that was, because like, yes, we go from lithium hydride and hydrogen, and now, so you think it's going to be an instrumental, like now we're going to do calcium, and now we're going to, but this was actually, to me, that made me kind of like scratch my head. And again, it came through the algorithm development. It came through using the quantum computer smartly for the things that the quantum computer was good for, and it leveraged the classical component in a very smart way to be able to reduce the depth ultimately so that we could do larger systems. So those are the kind of developments that we're seeing today.
I fully agree, and I think it's impressive to see the speed at which things advance. Again, maybe as a person who has a connection with chemists in the lab, I have to be honest, and we do the same. I mean, we run calculation on metal clusters and so on, but these are just, at the moment, is a proof of principle. Mm-hmm. We show that they can be run. We don't compute anything that is relevant to the experimentalist at the moment. We just show that we can do it, because maybe we can do one calculation on one structure. But if you want to compute something chemically relevant, you have to follow a reaction pathway. You have to relax your system. Maybe just don't look at an electronic states, but many electronic states. And this cannot be done yet. I mean, we cannot be in production, but this doesn't mean that there is not the potential there. And as you said, we have to start where we can. And for me, the very important aspect in all this is that, DFT, as I go back, DFT, Consham, functional, it's great, but in a way, it's a dead end. Sorry for, in the sense that, sure, we can develop a better functional, but in terms of novelty of innovation, there is not much there. Right. Instead, this field allows us to develop new theories, new methods, and think differently. And so we are, in terms of theories and algorithms, we're becoming quantum ready. So it doesn't mean that the hardware is there yet, but this allows us to make incredible advancement also for theories that can work very effectively on classical computers. So I think overall there is really an intellectual advancement that could not have happened without this technological advancement. So it's super exciting. Mm-hmm.
So you didn't know you were going to get brutal honesty today from the panel.
I'm so sorry. That's why they called me, I guess.
Those of you working on DFT, I'm sorry. Okay, so...
No, I work on DFT myself. I work on DFT myself, okay? So I'm not saying that in a way, do you agree when I say?
Oh, absolutely. No, I love it. So, but I did have a question as an experimentalist. You've sort of answered this, but at what point is it going to be useful for someone like me? We photoexcite nanoparticles and do catalysis with transition metal catalysts and try to save the planet. Am I going to be long retired before we see benefits from this?
Well,
I don't know. I think you should answer this question because I'm asking these questions myself. Maybe, you know what, my personal question, I'm not sure whether I'm going to solve the energy problems in my lifetime with quantum computers, but they will. So, my goal is to train the next generation. So that's my answer, but I don't know. Maybe I'm too pessimistic.
Yeah, I think there's a progression, right? So right now, we're done with NISC, which is great. We have logical qubit systems deployed. You can run robust calculations, but it's a small number of qubits. So like in our partnership with Atom Computing, we have 24, 28 logical qubits. That's on path to get to 50 at the end of the calendar year. And we're excited about that because now you've got a system where you can really start trying things out. You're not going to be solving chemistry problems on that you couldn't solve, on your laptop or on an HPC system. But as Jamie mentioned, the field is moving tremendously fast. In the coming years after that, we'll have 100 logical qubits. At that point, you can start to look at correlated condensed phase matter systems and ask questions or answer questions you couldn't answer before. And so we're starting to see a scientific advantage. I think when it's going to be practical to someone in a company, in a lab, is probably when we have on the order of 1,000 logical qubits. That's where you can really kind of do the pencil and paper work and show, yep, now we'll be able to solve some really interesting problems, put them back in the context of a reaction network or a catalysis problem, and get first-time right answers so that you're not wondering if the computer actually gave me garbage or not. So I think we see the roadmap for that, and it's not decades away.
And maybe I would like to add another thing. I think that to solve these big material science, chemistry problems, the task of the quantum computer or eventually the GPU with quantum chemistry methods is just one little portion. To solve these problems, we'll need to work with the experimentalists on a day-to-day basis, and we produce something, they give us a feedback, and they tell us, and AI cannot be ignored. Listen, I'm not an AI fanatic. I'm not a fanatic of anything. But I think it's very important. It's an amazing tool that we cannot neglect. And if it's used with knowledge and with criticism, the point is that these calculations that we will be able to do on the quantum hardware or on the super expensive HPC, they have to be just a minimal part. We cannot calculate everything there. We need AI to accelerate this process and experiment.
So I just want to mention, so I think that...
You are still coming to Chicago to give a seminar,
I
right?
am, yes.
Because
yes.
maybe she will not accept my invitation after today. I'm joking.
Yeah. So I will say, right, that we're starting to see evidence of what we have called at IBM quantum utility. So I mentioned these iron-sulfur clusters. This was done with a supercomputer, Fugaku, and then in collaboration with Riken. And then, again, part of it very cleverly divvied up the way that they solved the problem, part of it on the quantum computer, part of it on HPC. So I think that we're starting to get closer to that. There's another example that we showed a couple years back for a condensed matter system, and that one was really interesting to me because we were able to get some information out of the quantum computer that didn't match anything that was classically simulatable. So when we published this paper, and we did work with classical, scientists as well, computational scientists as well, right after we published it, there was like a flurry of different responses in the literature. And what was very interesting is that all of the different classical methods they applied, all of them had approximations included in them, and they varied by around 20%, right, of each other. And so you kind of like see these curves, and if you go to we have a session later, you'll see some more details on it, but you'll see these curves, and it's like, here's the answer from the quantum computer, and then you have these like data points like all over from like the classical models of it. So you might sit there and scratch your head and you go, okay, well, certainly the answer is fundamentally different. It's also not exactly the same as anything you get from a classical computer, so which one is right? You know what I mean? And what do you call exact? And then you start getting into the philosophy of it. So anyhow, fast forward, looking at the chemistry examples, I think what we've predicted is we've shown a couple of examples of utility. Those are going to continue to come out. We're going to start seeing like a library, if you will, of examples of these, and they'll accumulate over time. And we actually think at IBM that we will see something that's called quantum advantage, which is where you can perform a calculation faster, cheaper, or more accurately than using a classical computer alone by 2026.
Okay,
so
then I will still be alive. That's great.
You will still be alive, Laura.
We hope. All right, so Laura, you mentioned AI. I know some in the audience may have heard of machine learning, artificial intelligence and chat GP something, and DeepSeek. So maybe the panel could talk about, is there an intersection of quantum computing with AI? And if so, what is that?
Yeah.
Absolutely, yeah. So right now, and I'm going to focus on how quantum makes classical AI better. There's another side to this question as well we can address, but right now, classical models for artificial intelligence, so-called machine-learned potentials, machine-learned force fields, as Laura mentioned, they've done wonders in the field. I mean, they can compress search times by 3 orders of magnitude or more. If you're screening materials, you're screening small molecules, you're simulating dynamics, they're just tremendous. I like DFT.
I love DFT too.
And they're trained on DFT, largely, yes. Right? These models that we built. So what that means is if you're screening, material candidates or molecular candidates for you, and you kind of think of the traditional screening funnel, that funnel's leaky. Those AI models are only as good as their training data, and as Laura mentioned, the training data is not perfect. It can do pretty well, but it's not perfect. So I think one of the first big impacts of quantum computing for everybody, right, experimentalists, computational folks alike, is going to be making those AI models better. You'll probably still pre-train them on DFT, but now you'll have, in some cases, ground truth, exact answers. So you get the benefits of the speed of AI in this space, but as you start to integrate in quantum training data, you also get the benefits of accuracy. And so it really becomes, I think, a virtuous cycle of quantum making the AI models better, driving you into new parts of chemical or material space, doing new quantum calculations, and it becomes a flywheel. So that's one side of the question.
Like, how much time do we have? So I think there's an intersection of, AI with quantum for sure. There's a couple of different ways you can look at it. You can look at it as quantum models for classical data, quantum models for quantum data, and then classical models for quantum data, right? And so a lot of those, there's still a lot of really active research in, I would say, like, again, going back to this concept that, really smart people have the intuition that have been working in this field for quite some time that quantum could bring an advantage here. And we've seen some of that evidenced in some of our, the theory work that goes into why you would even think about quantum machine learning. I would say just from a very practical standpoint, we are already applying AI for quantum today. So just, to think about, I mentioned earlier, the circuit is kind of the magic, right, in the algorithms. And sometimes when people are getting started with things like Qiskit, which is our software development kit, our software stack, they may not know necessarily like how to code and might want some help with that. So we have, at IBM, we have some code assistant work that's based off of LLMs and AI for that purpose. So that and sort of circuit optimization as well. So those are the types of tools that we're developing that are sort of on the classical AI, like to help with quantum. And then I'd say the rest of it, very much research areas, but certainly some reason to believe, that things like HHL algorithm, for example, and there's all sorts of different algorithms that people are exploring today to see what you can do with quantum for AI, and then again, quantum models on quantum data, which is like a whole nother world, because you have to think about what quantum data even means. Like, what is that? So anyway, not to go back to philosophy, but...
Yeah, I think I would like to add one thing that, this is extremely important, and this is how progress will be achieved. We have to combine all these tools. We have, as a community, I think we have a responsibility, a moral responsibility, to make sure that the quality of data that we produce is acceptable and reproducible. So, for example, with our journals, we are really debating how to implement a system so that data are always reproducible from other groups, people can trust them. And so I think this is also important for us, not just say, okay, we have this amazing tool, incredible tool, we are so powerful, but we want to produce reliable, trustable data.
Yeah, and quantum too, right? Like a single experiment doesn't mean you should go to the headlines, right? Like not to, going back to the hype kind of thing. But to rather look at it like very from a fair standpoint with the reproducibility kind of as well, taken into account from an experimental standpoint.
Are we getting close? Okay, so maybe one or two more questions, quick questions, and then we'll get to some audience questions. So crystal ball time for the panel. What's holding us up? Is it we need better qubits? We need to improve the coherence among the qubits, or is it an algorithm issue? All of the above. Maybe we could panel could address some of what's holding us up from getting to where we want to be in a reasonable time frame.
I have maybe actually I want to suggest one point that for me is, so what about the temperature at which these devices can function? I mean, is this one of the problems that we have to address? At what temperature can I solve the Schrödinger equation on a quantum computer?
Yeah, maybe you could say what temperature your computers run at.
So I mentioned before, the superconducting qubits all have to run at very low temperatures, so it's around 15 millikelvin, right? So, it's not just temperature, right? Like we need to think about, when we're thinking about systems, it's scale, quality, and speed, right? How much can you scale? How many qubits can you get? And how do you connect them together so that you can run circuits that are of interest? And then quality, what kind of error rates do you have in the qubits themselves? So making better qubits, right? And then speed, being able to do gate operations in a fast fashion and being able to have a universal gate set so that you can run the circuits that you're interested in. I think those are the components that I think are really interesting and important to have in it when you're considering any type of hardware. For us, we have put out a hardware roadmap. We have taken into account error-correcting codes that we think are going to be important in the future. We have, kind of thought about LDPC codes as being where we're going with it, and we're designing our devices so that it has the right connectivity so that we can run those codes. So we're already thinking about, how are you going to be able to run more and more complex circuits? I think that the holdup, if you will, in my personal experience, is when you get people together in a room that don't speak the same language. You have the quantum, expert who knows about quantum circuits and quantum algorithms talking to the classical expert who's focused on the classical algorithms. And then you have people from industry who understand, the bottlenecks that they have in their own calculations that oftentimes are highly tuned for the systems and the problems that they're looking at. And they all speak different languages, and they all, might even have a different sort of reason why they're using quantum computers or exploring them at all. So in my opinion, it's really easy to stay high level and to be able to talk and talk, but what's really the bottleneck is getting those people to sit down in the room together and crunch the numbers and actually do research and figure out what you can do, what's possible, and overcome that language barrier.
That was a great answer. I mean, my first reaction to your question was also people.
Yeah.
People and language barriers. And I think,
it's always the people, right?
it's really hard to transfer knowledge across those domains. And I know that IBM's developed AI tools. We've developed AI coding tools to try to reduce some of the barriers. But at the end of the day, the difference between disciplines, we just need more cross-fertilization. The only other thing I'll say, because this started with temperature, is not all qubits have to be cryogenic. So there's a whole range of qubits out there. The neutral atom systems work at room temperature. The topological systems require tens of millikelvins. Some things need to be in the Dill fridge, some things don't. But there are a lot of choices out there, which again, I think is what makes the field so exciting, is to think about, the platform approach with different flavors of qubits for different problems with different sort of scaling, speed, and reliability criteria.
Yeah, you had me worried. I was going to have to do some major house renovations to fit the dilution refrigerator into my basement, so I could.
And don't forget the helium.
Run my yes, the helium. That's probably the easy part, actually. Okay, we wanted to save some time for audience questions. If there are questions, please come to the mic and go ahead. Yeah. just shout it out.
Okay, thanks for this panel. Actually, my question about application and for chemistry. So for chemistry here...
Or lower your microphone a little, just a little. Okay, great.
Okay, thank you. So for chemistry, we know that the near-term application is going to be the chemistry application. You can hold it. Okay, so the chemistry application is the near-term application. And say in the near future, we might have like 50 logical or 100 logical qubits, but the qubits are still fragile, that really, even with the error correction, we need to really have a shallow circuit. Most of people have been using VQE, which we know is not scalable. Adaptive VQE, it has a problem with the overhead of the measurement. Quantum phase estimation is really far term. Even quantum filter diagonalization is also still far. So people also have tried a lot of tools that is to stay away from VQE, but still very, very classical. So what is really needed to develop better algorithms to be ready for when these qubits are ready as well for chemistry applications? Are we doing this wrong because we are just really trying to quantize classical algorithms in quantum chemistry? Or there's, like, how we should think about that?
I mean, if I think about the problems that we are trying to address now, of course, the algorithms probably have to improve. But I think it's also very important to distinguish. So think about your problem, your chemistry problem, and ask yourself what really needs the quantum computer and what can be done on the classical computer. And I think that trying to do on the quantum computer what you can do very efficiently on the classical computer is probably not the best way to go, right? I don't know, do you agree?
Yeah. I mean, we have to get VQE has been very useful, right, to study, but I think that there's other approaches that, like Laura is alluding to, where you can leverage the power of a classical computer to really help you get away from VQE and get away from the measurement overhead that comes with VQE. And so, and again, you need to think about how to use a quantum computer. You can think about using it in a different way than what a VQE type algorithm would have you do. So we have some examples of this. I'm going to make a plug for our session up in Ballroom 20D, I think, happening at 2, where there will be a little bit more in-depth, discussion on that as well.
Hi, I'm Jay Suarez. I lead the Scientific Advancement Unit at the ACS. Hi, everyone. Yeah. Fantastic talk. I'm going to set an aspirational goal. We're a mission-driven organization, and I feel quantum gives us hope of solving some of the issues in our lifetimes. So I'm riffing off a talk you gave earlier, Nathan. 96% of products manufactured have a basis in chemistry and material science. So that's huge. Quantum has the power to do life cycle assessments on the production or prediction of each of these products. And so where I'm getting at is a sustainability metric being an ultimate goal, where a number on each product can drive consumer confidence in purchasing or consuming. That could be transformative. So how far are we from something like that? I'm quoting John Lennon's Imagine, but you know.
Wow. Yeah, that's so we think about a lot of these things from the perspective of reaction networks, and we build tools today that allow us to quickly go through and look at the sets of reactions associated with the degradation process. Right. Whether it's something sitting on the shelf degrading, we're reacting with other components, whether it's something in the atmosphere, degrading because it's interacting with ozone and oxygen. And by building out that tool in collaboration with the Ryer Group at ETH Zurich and PNNL, it became also a really useful diagnostic for when you need quantum and when you need quantum computing, because there's a Jacob's ladder of theory that you need to climb, right? And we can do a lot of that reaction network exploration with DFT, maybe 1 million steps. We find for about 3,000 steps, we need couple clusters, singles, doubles, triples. And then for maybe a handful, tens, so let's say 20 to 50 steps, we need full configuration interaction or some sort of CAS-CI type of approach. But the framework's all there. And as we can start to offload maybe less CAS and more full CI onto a quantum computer, that framework's going to take advantage of the accuracy that it gives us. Is it a sustainability metric? No. But it's a step in the right direction for being able to ask questions like that about products, about what happens when you release a coolant into the atmosphere. And quantum will plug in as an accelerator in the same way that AI will. And of course, HPC is not going anywhere. You have to solve the physics-based equations.
Can I ask a question on that? How much does HPC play into that today?
Not a whole lot as far as I'm aware.
Right.
So, we talked to a lot of federal agencies. I think one of the holy grails here is to develop a consumable number or something that a layperson can consume and understand. Mm-hmm. And so getting to that metric, that single metric, would be hugely transformative. And everyone has their different parameters. What's the truth? It still needs human curation, but we can have a very long conversation. But the Office of Sustainability is under my remit, and we have a lot of tools available. But bringing them all together in one complex calculation and then put systems thinking on top of that, that sounds more quantum than HP.
But I think that the combination of quantum and HP should end as you said, the supervisor, the human supervisor with the brain, and should also help to really distinguish when you need this powerful weapon or when you can solve a problem, not even with DFT, with classical simulation techniques, and I'm saying classical molecular simulation. So I think that's very important to understand that we are not trying to solve only one type of problem. We are solving a multi-scalar problem, and we need to combine all these methods with the brain, with some human chemical knowledge.
Yeah, I would say the sustainability question is certainly multidimensional, and it's a very complex and, it's an interesting issue. So I'd be happy to talk anytime because ACS has the power to convene, but I'm not going to take over the microphone here.
Hi, my name is Vibhujan. I had chemical synthesis and material science business for Millipore Sigma. We sell millions of products, and in last 6 years, our focus was how to get thousands of reactions, which our chemists do every year, and get into automation and AI. And I read about, Nathan, your work, and then my question was, for quantum computing, what should be the approach for a company like us? Should we wait and watch, and how we can enter into the space? What we should do with the companies like IBM or Microsoft?
Well, if you believe us that the biggest problem is divides between disciplines and information transfer and, speaking the same language, then getting quantum ready is the right thing to do. Would you use a full quantum computer today? It depends on the skills you have. It depends on the capabilities of that computer. But getting ready for this technology coming and, starting to use frameworks where quantum can be naturally integrated it's an easy path to take. It gets you ready when these disruptive changes are going to come, and it adds value in its own right.
Yeah, and I'll just add that we've done our best, at least at IBM, to reduce that barrier to entry as much as humanly possible. So this is through a number of different ways. One is that we've been working with partners to add function layers onto Qiskit so that people who are coming from a chemistry background, for example, have something that's more familiar that they can look at to get started. That's one thing. The second thing is, we put a quantum computer on the cloud in 2016. So it was a 5-qubit quantum computer at the time, but anyone could go and sign up for it and start trying it out and start looking at the gates and understanding what a Hadamard gate or what these different operations are and try making quantum circuits. So we still have that. We call it open access. Anyone can go and use 10 minutes on a quantum computer today. 10 minutes, by the way, is plenty of time just to try your basic algorithms out and just see kind of what happens and get used to it a little bit. But I do think that starting earlier as opposed to later is best because you get in at the ground floor you can understand the evolution and advances when they come out for what they actually are with an educated lens on that. That's my biggest fear, actually, is that, you know, we're going to show an example of quantum advantage and no one's going to understand what we did, honestly. That's what keeps me up at night. So I think, you know, the more that people have that education, it takes a long time to wrap your head around these things. It takes a long time to understand the different algorithms and where to use quantum and where it makes sense and how best to divvy up these workloads, how to use HPC, like all of that together. So I think that that education component is very important. So getting started yesterday really is the right way to go.
Yeah. Thank you.
So, hello, thank you for all the panelists for sharing your time with us. So as a graduate student who just started their scientific career, and as somebody who also works in, you know, interdisciplinary field of using quantum algorithms to try to solve for quantum chemistry problems, I wanted to re-ask Professor Kraus's question because I think people isn't, you know, the only answer, and I understand, I can see both perspectives, you know, from academia and industry, but realistically, should we be cautious of the promise of quantum computing, or fundamentally, are there any engineering issues that are preventing us to achieve to, you know, the quantum advantage, or like what should we do as a young scientist trying to actually solve problems, which is something, you know, I want to, I guess, hear.
So I think as a student, right, there's a lot of things that I'm starting to see, including like a lot of universities having courses available, so quantum computing courses, master's programs, accreditation programs, and things of that nature. So my advice, like from that standpoint, is like, why not, you know, take that if that's a part of the opportunity that's there, and then you can see for yourself like what you end up, you know, doing with that and where you end up going. I think that, you know, there are still some open science questions, certainly.
Yeah.
One of the things that, you know, that is very interesting too is that we've talked a lot about qubits and the quantum computer, but there's this whole infrastructure around it, right, that helps support it, these control electronics and things like that. And some of that is really energy intensive. And so we're looking in some ways towards academia for some of these key components like optical to microwave transducers, for example, we just don't have right now. And if we had something like that, it would reduce the element of energy cost down quite a bit. That's used not just in superconducting qubits, but, you know, spin qubits as well, a similar infrastructure. So I think it could be applicable to a number of different architectures. Okay. That is an example. So there are still open science questions. And then there are, on the other side of it, there are things that you look at, like with our roadmap, and you say, this is on an engineering path at this point. We're not going to be changing the materials that we're using for our qubits, right? We're no longer like looking for that next best like material, if you will. So now we're really working towards like, how do we scale? How do we get, you know, the error correcting code to work and all of that? So although I still fundamentally believe that we need to speak the language, I think the courses that are available for people today will help with that quite a bit, because you'll learn it from the beginning. It's not going to feel as foreign to someone who has already graduated and didn't have that opportunity. And in the meantime, recognizing when something is truly an industry engineering challenge versus an academic science question.
Right. Okay. All right, so excited to, I guess, for Microsoft and IBM's future developments.
Yeah, I think a lot of things have been distilled down now to engineering challenges, and you know the activity that DARPA is doing, for example, with the underserved systems for utility scale quantum computing, is doing a very systematic evaluation, excuse me, of what it'll take to have utility scale quantum computing in 2033, and a lot of it boils down to roadmaps and engineering challenges. So I'm not worried about the fatal flaws in there. I think, you know, there's certainly hard work ahead, hard work on the platform system side, as well as hard work that needs to happen on the algorithm side. Those two, one can't stop and the other one goes forward. They both have to progress, but it's a very exciting time to be in quantum, and I wouldn't be worried. I'd be thrilled about what's ahead.
I have one last question, I promise. So I'm thinking about Laura's comments and your comments about quantum technology. If you could, each of you, Microsoft and IBM, what would you say is the biggest challenge you have solved using quantum computing for the chemists today?
Hopefully it's not the hydrogen atom, but go ahead.
I mean, like solved, like literally, I'm trying to just like, what are, yeah.
Do you mean like what problem they have solved?
Okay, the biggest contribution I think that we have made is making quantum computers so accessible to people. That is like, I mean, you don't have to know a quantum engineer to be able to run, you know, a circuit and try it out. And so that, I think, has been a very, very big thing that we have accomplished at IBM. You can access quantum computers over the cloud. You can run them today. You can use them in classrooms for education. And I think that that was an unsolved problem before we started putting it on the cloud in 2016.
I think ours has to be the topological qubit, right? Almost 20 years of investment in Microsoft, longest running research program there. And the whole point was to address a version of those three criteria you heard before: scale, speed, and reliability. Digital control of the systems. You can fit 1 million qubits inside a single DIL fridge, which means you don't have to worry about networking between cryostats. And you know, the speed that's actually going to allow us to run deeper circuits and do more complicated calculations. And it was a long journey. It was the materials side of the journey, then it was the measurement side of the journey, and it's now, as we talked about last week at APS, it is starting to realize measurements to do X and Z type operations on the system. That's really, I think, going to change the way we do quantum computing.
Hello, thank you, panel. I'm Sam Stomerner. I teach undergraduate physical chemistry over at Point Loma Nazarene, just across the harbor. And I'm thinking about my next fall's quantum chemistry course. And I want to put this out in front of my students, expose them to this, show them that, you know, this is an option for grad school. I'm excited to hear about the open access option, but are there any other resources or tools you'd recommend to really put this in front of them, make this feel like it's a tangible, practical thing that they can touch right now?
I mean, so for example, we have a quantum chemistry, computational chemistry class, which I teach, and it's more quantum chemistry method. Usually, it's more theory, and we use them on a classical computer. But now, for example, with Johanna, we give some tutorials to the students using Qiskit, for example, in which they can create their gates, very simple ones, and they can see the evolution of the operation. So I would certainly suggest that you look at Qiskit. There are a lot of tutorials that are very good. And then maybe, I mean, either you or, but also you are a theoretical chemist, you know a lot about chemistry, so you could perhaps in your class give more of a research talk in which you show what problems need a more powerful hardware that cannot be solved today on classical computers. So try to engage them in the research aspect, in what difference that they can make if they embrace this career.
Thank you.
So Laura's been bracing the honest in her questions of quantum computing. And I think actually, you know, I feel Nathan and Jamie have been very subtle and very polite in your own questions of chemistry. I mean, it's kind of, you can see it in this, hear it in the subtext of some of the stuff that you say. But I would invite you to, you know, to ask the questions of chemistry. What is it? I mean, because I think Nathan, you said, you know, basically this is a revolution in computing. We've had this, you know, we've had the abacus for a long time. Is it reasonable, for instance, to think that we bring in a tool of this kind of revolutionary capacity and expect that chemistry itself as a field might not have to change in some way to really take advantage of this tool? And so, yeah, I would like to hear your reflections, thinking, well, if you really want to maximize this, well, then there is some responsibility as well, perhaps. There are some questions to be asked about the practice of chemistry in the chemical enterprise.
Yeah, that's a great question. I think there's two massive changes coming to chemistry that feed off each other. The first of these that we're seeing already is AI, right? But as a computational chemist, I feel comfortable saying that people don't believe us all the time. Why don't they believe us all the time? Because, as Laura mentioned, our models are simplified, our theories are approximate, and, you know, oftentimes we're off by, you know, a few millihartries or more. And so the answers we're giving simply aren't predictive. So these two technologies go together. AI will drive the field forward. It'll change the pace and maybe the space of things we can search. But it's going to fall flat. It's not going to realize its full potential if we can't equip it with the accuracy that it needs as well to deliver reliable predictions, first time right predictions. And so I think each of those by themselves might be a little bit disruptive, but altogether, hopefully it will change the way we do chemistry by opening up doors to whole new areas we just couldn't explore before because of scaling issues or accuracy issues.
I think I'm going to show my chemistry background, but one of the things that I had to learn was a conversion between kcals and millihartries.
2.5 kilojoules per mole.
Still thinking kcals per mole, always, and I always will. But yeah, like being an experimentalist, right? This was oftentimes my experience is that, even with AI, you wouldn't be able to account for all the parameters that we needed to. So for example, you might be able to account for solubility, but then you forget about safety. And so I'd get answers back with literally like TNT to use for, like a battery electrolyte. So, and I don't want to diminish it because there's a lot of sophistication that goes into this, right? And there's always this exploration. And I do think that that's part of why it's going to be important to have that sort of experimental validation piece of this as well, like along the way, so that you can constantly check your answers, because even if we check for a theoretical molecule against some exact result, like what does that really mean? And to your point, Laura, like where is the actual, chemical molecule that someone cares about, or a reaction coordinate that someone cares about that's going to change the catalyst design or whatever it needs to take, right? So that's, I think as a field, like one of the things that we're going to have to start doing again is coding. And having that be a very active part of our education, because it's going to be so important for the types of work that we're doing as we're now having these sort of heterogeneous architectures available to us for compute resources.
So maybe I can add something. I always like to when I design a project, I want to start always thinking about the problem. What is the chemistry problem? So chemistry is at the center of our society, okay? And if we're all here, we all believe in this. And we have incredible challenges to solve as a society where chemistry can help. And they are related to health, they are related to climate, whatever we believe in climate change or not, climate growth or sustainability. And so if I want to solve the problem of excess of carbon, which it is there, okay? People may not agree politically with that, but we have excess of carbon, excess of methane, and we have to try with our chemistry tool to address these challenges. So the question is, how can we incorporate this technology? And I think that in a way, we as chemists, now that we have this powerful tool at our disposal, maybe not right now, but in 26 apparently, with AI and more experimental data, how can we use all this to address excess of carbon or neurodegenerative diseases, for example? So I think we have a lot to work on as a community, and so this is exciting that we can make a difference in this new way.
Other questions? Please don't be shy. You have your chance. I tell the graduate students when someone's defending their thesis, this is your last chance. You have the experts here. So pummel them with questions while you can. While you think about that, I have a sort of practical question for the corporate folks on the panel. So IBM, last I checked, and Microsoft, they're for-profit companies. So at some point, one would think you're doing this to make money on it, and a quantum computer sounds expensive. Just ballparking the single computer, if you have a Illusion refrigerator, all the electronics, hundreds of thousands of dollars per computer or more. Is it more?
It's more than that.
More. Okay. Well, that makes it worse. And then helium is getting more expensive. It's rare, So, is there a point where Microsoft or IBM says, we're not going to do this anymore because it's not going to be profitable? And what's that horizon? And and then who will? Is that even on the radar at this point, or is the promise so good that they're going to keep putting in millions and millions and millions of dollars for these things? I think the audience wants to know.
Well, we've used the phrase utility scale a couple times. It's probably worth defining that, right? So utility scale, the notion of utility is when the cost of developing a computer is offset by the value it produces. And I think that's a really useful way to be thinking about this space. It doesn't require a demonstration of quantum advantage necessarily. It demonstrates value coming from the system. And so that's the way DARPA has been analyzing it. I think it's a really nice way to frame the question. And we believe value will come from these systems, right? The tech industry is not known for its attention span, and we paid attention to this for 20 years. And the future is exciting. So I think that's the right way to frame it, is when does the value overcome the cost? And you think about chemistry, 96% of manufactured goods, that is a huge market. There's a ton of potential value there.
Yeah, it's funny. I never thought of it in dollars before. I've never defined utility that way, but it's interesting. I think of it more from like the science standpoint and like what you're actually getting out in terms of answers, but it's interesting. But what I will say is that this is part of the reason why we have done the work that we have to make quantum computers available over the cloud, so that you don't have to literally have a quantum computer in your cafeteria like Cleveland Clinic does. Or in a chapel like RPI does, interestingly enough, but you can still be able to afford access, right? So we're thinking about it more of like, how do you, depending on what you're doing, whether it's for education or whether it's for research, you probably need more time on the quantum computer because you're optimizing things and you have to go back and forth. And, once you're at publication time, then you're really going to use it intensively as you're trying to get reproducible data, right, for your tables and your paper. So I think, depending on, where you're at and what you want to do, you're probably going to need a certain amount of exposure to it. And so you can just, basically the way that we've set it up as a model is that it's by time. And so you can basically pay by the minute if you want, or you can buy it in bulk and then use it as you need to. So that's sort of, I think, an approach to that, even though, the quantum computer itself might cost tens of millions of dollars. That's not how much you're paying for actually using it as a scientific tool.
So I also want to get back to, a theme I've heard is at some level education and educating people and interdisciplinary education of people. If I'm in chemistry, I want to focus this on chemistry a little bit. What are the pressure points that need to be, how do I get in, on the material side? I heard mention that you don't have to worry about the qubits, we're just engineering things. When I hear engineering, I think, okay, the problem's solved, I go on to something else, as a fundamental scientist. So, what, maybe as a more fundamental problems, what problems need to be solved that we can work on, as a community at the basic level? That's not, chemical engineering is a different field, right? But, or are there problems that are solved that, and we can just really basically just engineer this thing with a little bit better circuits and a little, make things a little warmer. What problems should we be working on as chemists, experimentally or theoretically?
I'm just saying, for example, when we do materials discovery for a given application, we look at variations in the composition of the material, and that requires the chemistry brain. You don't just try things randomly, you do it in an educated way. So I think this is a problem which we can focus as chemists, as material scientists, and it will benefit from this architecture. If this was the question, yeah.
And I didn't mean to minimize the engineering challenges, by the way, that we have in front of us to accomplish what we've set out to do. There's a lot still there. But I think you've heard me say it before, and I really think that it's important to go back to sort of the algorithm development. And then also we have an opportunity as a chemistry community to have a guiding light. We can work with experimentalists, understand where the problems and bottlenecks really are, and look at solving those problems. Because if they're a solved problem, if they're easy to solve classically, then why use a quantum computer for it?